So today's lecture will be about force and torque sensors. That's one of the important topics for a mechanical engineer, because in many machines you need to measure the force that you have on the frame, or you need to measure some deformation that you have on the frame. And in all those applications you can use force and torque sensors. First of all, we will see sensors that do not measure force directly, but I will show you only sensors, only one of them, that measures deformation. So we will transfer the force that we actually have into deformation of an object, and then we will measure this deformation. So here is an example how this works. So let's imagine we have a beam, and this beam is fixed at one end, for example here on the left side, and on the right hand side as well, and we apply force. So this part of the beam is under compression, and the top part of the beam is under tension. And the sensor for force is shown here in yellow, and this will be the strain gauge. So the strain gauge is the most common sensor that is used for force measurements. It will be also used in torque sensors, but it is not the only way how you can actually measure the force. Here is an example how such a strain gauge looks like. There are many types, but this is just one of them. And here we see that the tension that we apply tries to make this distance bigger, tries to make this strain gauge longer, and this will change electrical resistance. If we apply compression, then this will lower the resistance of the strain gauge. The gauge in ideal case should be not sensitive in this lateral direction. So if you want to measure the force also in this direction, you need to apply another strain gauge that is oriented properly with respect to the force. Let's take a look on the types of strain gauges. We will be discussing two types of strain gauges. One will be made from metal. We'll call that a metallic strain gauge. This strain gauge is based on a wire or a foil of some special material, as we will see later. Here you see a few examples how this metallic strain gauge looks like. And the second group that we will discuss will be a semiconductor strain gauge. And here again you have an example how the strain gauge looks like. We will focus mainly on metallic strain gauges because they are the most common ones. And I will show you only briefly the properties of semiconductor strain gauges and how they work, and what advantages and disadvantages they have compared to the metallic ones. Let's take a look on the construction of a wire strain gauge. So this is how the strain gauge looks like. So it's a thin backing material, and on this backing material there is either a wire or a thin foil. So here on the left picture you have an example of a wire. So this is the backing material. The backing material can be paper, it could be a polyamide material or some other kind of plastic material. And then here in this wire strain gauge we have a very thin wire that forms this shape on the backing material, and all this is then encased, and it is installed on the beam or on the device wherever you want to measure the deformation. So if you buy a strain gauge, it looks like this. This is the strain gauge itself with the backing material. Here you have two terminals that allow you to connect the strain gauge to the electric circuit, and then this is a tape that holds the strain gauge during installation. Strain gauges are glued with special glues to the surface. The surface needs to be prepared, so it's not just take the strain gauge and glue it, but it needs a detailed preparation. In the case of a foil strain gauge, it looks like this. Again, it's a backing material. In this case, it's typically polyamide material that is used, not paper. And there is a thin foil of the special coating material. The material in both cases is called Constantan. And again, this is the shape, how it looks like. And here we have two terminals that allow us to connect the strain gauge into a circuit. In both cases, the sensitive direction in this picture, it's from left to the right, like this in the horizontal plane. So this is where it is sensitive. It's not sensitive in the vertical plane, like this. And in this picture, again, the sensitive direction is this one, the vertical one here, and it should not be sensitive in the horizontal direction. So both possibilities are available on the market today. The foil strain gauge is the dominant type, simply because the manufacturing process is much simpler. The strain gauges are produced with a process that's very similar to the production of printed circuit boards, so that's etching of the thin foil. So originally it starts as the backing material that is completely covered with the Constantan layer here, and then the shape is created by etching away the material where you don't need it. So it's a repeatable technology. It's quite fast. It's much easier to produce it than the strain gauges here made by the thin wire. Here are a few more examples how the strain gauge can look like. So far we've seen only examples with a single strain gauge, but in many cases you need to measure the strain in multiple directions. So of course you can use multiple single strain gauges, but in this case it's difficult to maintain the correct angle. So there are so-called strain gauge rosettes. On this picture you can see an example of such strain gauge rosettes. We can see that they come in many sizes and in many shapes. So for example, here we see a strain gauge rosette with two strain gauges. Here the angle is 90 degrees. Here we see another strain gauge rosette with three strain gauges, and here the angle is 120 degrees. Here we can see the same but with four strain gauges. So it really depends on your application and where you need to use it, and if you need to measure only in a single direction, and if you already know what this direction should be, or if you do not know what is the direction, and then you have to use the rosette, measure in all three directions, and calculate what is the main stress direction in your application. In the picture on top right you can see another example of a strain gauge rosette. This is a special strain gauge rosette used to measure stress in the material after heat treatment. I'll have later some example. So here we can see that we have three strain gauge rosettes. This is a mill, and the procedure is that you mill a hole in the middle, and this will release the stress, and you can measure it. So all those strain gauges work on a very similar principle. The principle is shown here on this picture. We are looking for the electrical resistance of the strain gauge, and we are looking how will this electrical resistance change if we apply some strain. So let's imagine that we have a beam, looks like this, and here initially this beam, this piece of material had some length L, and now we apply some force and we extend the beam by some delta L. In reality, this is a very small extension. Of course, this delta L is a very small value, but as we'll see, it's possible to measure with strain gauges with a very high accuracy, even the smallest changes. So if we apply the force here, well, we will increase the length, and at the same time we will decrease the cross section. So if this would be a piece of electrical wire, then we are making it longer, and we are decreasing its cross section. So if we look at the electrical resistance, this is a formula that allows us to calculate the electrical resistance. L is the length of the wire, A is the cross section, and ρ is resistivity. It is a function of material, so it's different for different materials. So the strain gauge works in the following way. Here we have the strain gauge when we do not apply any force. It has some length, and obviously the wires will have some given cross section. If I apply tension here, I will make it longer by some delta L, and I will decrease the cross section of the wires. So in this case, I'm making it longer, and so L is increasing and A is decreasing. So we will increase the electrical resistance of the strain gauge, and here when I apply compression, I will decrease the length by some delta L minus, and I will increase the cross section. So in this case, L is smaller and A is bigger, so this will decrease the electrical resistance. However, we are not looking directly for electrical resistance because we are not interested in the absolute value, but we are looking for a change of this resistance as a function of strain. So we can define strain as the change of length, so this is delta L over L, and hence we are looking for a function that describes how is this change of electrical resistance a function of the applied strain. So now let's take a look on how we can find this function. So it is obvious that we are changing length, we are changing the cross section, but we are also changing the electrical resistance. So in some cases, for some materials, when you apply strain, it will also change the electrical properties of this material. So here this resistivity will change as well. So we have to calculate the dependence of resistance on all those three components. So change of resistance as change of length, change of cross section, and change of resistivity. So if you calculate the partial derivatives, you will get those formulas. So for example, here we can see that it is telling us how resistance is changing as a function of length. This is a constant value, so ρ over A is constant in this case, and then we have some change of length, and similar fashion we can create the two other equations. If we substitute those three equations into the formula for delta R over R, this will tell us what is the sensitivity on all those three components, and we can see that here there is some sensitivity on the change of length, some sensitivity of change of cross section. Note here the minus sign. This is coming from this part, this formula here, the minus. And then there is a change of resistivity over resistance. And then when we combine all those three formulas together, we will get the resulting equation that is telling us how this is influenced by the three components. First of all, before we do that, we will try to simplify even further. It is clear from this picture that if I apply force, then length is increasing and cross-section is decreasing. And also if I apply compression, then I would decrease the length, but I would increase compression. So there is definitely a dependence between length and cross-section in this case. So this is described by a constant that is called Poisson's constant. It is again a material value, and this will allow us to simplify more the equation, because we will remove the cross-section from the equation, and we will just use the change of length. So this is the formula that we will use. So change of cross-section depends on the Poisson's ratio, and this is the change of length. The Poisson constant mu is material dependent, and for technical materials it is usually in the range between 0.2 and 0.5. So for example, if you have steel, it's 0.3, aluminium 0.33, rubber 0.5. So we can use this number to simplify the resulting equation. And remember that we are looking for the dependence of change of electrical resistance as per applied strain. So here this is my original formula, just written from 2 slides before, and here we have replaced the part with the cross-section change, just with the delta L over L, and we are keeping the resistivity changes. So the final formula looks like this. Here we have the change of electrical resistance. This is strain, and in this bracket this is the formula here that we have just created. It is just reorganized a little bit. It is reorganized because here we can see 2 effects. The first bracket, the 1 minus 2 mu, is coming from, let's call it, pure geometry, because here we do not have any electrical parameter. This is the Poisson's ratio. And here the second part of the bracket is dependent on the resistivity, and this is called the piezo-resistive effect. The reason why we have separated this into 2 parts is the following. The pure geometry is the dominant factor for metallic strain gauges, and the piezo-resistivity is the dominant factor for the semiconductor strain gauges. So for semiconductor strain gauges, the majority of the change from the applied strain will be created by changes of resistivity here, and only a very little part will be the pure geometry. But for metallic strain gauges, this part of the equation is very small, negligible, and this part is very large. So we can see that there will be 2 different effects based on the material, and that for the metallic strain gauges it is this part of the equation that is the dominant one, and for metallic strain gauges it is this part of the equation that will play the major role. In both cases, luckily, we can see that this is a constant, so mu, Poisson's ratio, is a constant number, and we can find out what this value is. We can do the same also for the piezo-resistive strain gauges, so for those strain gauges that use this part of the formula. Again, it will be a constant value, and we will call this constant a gauge factor. It is nothing else than the sensitivity, so this gives us a linear equation. We can see that here the change of electrical resistance is a constant value times the strain, and we can find out what this value for the constant actually is. I have to say that for the semiconductor strain gauges, it will not be just this simple equation, because there is also dependence on strain that is nonlinear, and we'll see that this will be one of the problems of semiconductor strain gauges. But for metallic strain gauges, this is a linear dependence and this is a constant value. Here we have a few examples of the gauge factor for different materials. Not all the materials that you see in this table are really used in strain gauges. For example, just by looking here on the platinum that's pure, we can see that we have sensitivity of 6.1, which is larger than the other materials. So just by looking on this table, it would seem like platinum is a good material for strain gauges, but it is not. The reason is that platinum has a significant temperature coefficient of resistance. So in other words, a platinum sensor is a good temperature sensor, but the temperature is changing the resistance. So if we have temperature changes, then we will not be able to measure force changes, because the force changes, this value of change of electrical resistance will be much smaller than the value that we have created by the strain that we are looking for. So platinum is not an ideal material for strain gauges, and we are looking for material that does not change its electrical resistance with temperature. And one of those materials is constantan. Constantan is an alloy of copper and nickel. Here you can see the composition, so 55% copper and 44% nickel. And the sensitivity, the gauge factor, is 2.1. It varies a little bit with the composition, so if the composition is different, then the strain gauge coefficient, the gauge factor, will be different as well. But we can say that the gauge factor of metallic strain gauges is approximately 2. You will find it always on the package of the strain gauge. It varies a little bit, so it can be 2.08, 2.09, something in this range. Anyway, it's close to the value of 2. Here the other materials are used as well for strain gauges, for nichrome, karma, and so on. You can see here the compositions, and some of them have some trade names, but basically it's the very similar alloy with a very similar properties. So we're looking for some alloy that has a good reaction to temperature. In other words, it's not changing the resistance with changes of temperature. From this table, we can see also that nickel would seem like a good material for strain gauges. The sensitivity is negative, but this is not a problem. It looks like 12. Okay, that would look very nice. But unfortunately, if we look on the dependence of the gauge factor or resistance versus strain, we'll find out that it's non-linear. So we can see that on this chart, the negative sensitivity would correspond to the origin here. We can see the negative slope, so it is decreasing resistance when we increase the strain. And then we have an area where the sensitivity is very small or 0. And then in this area we have a positive sensitivity, and here we have a linear dependence. So the nickel is not a good material by itself. We need an alloy of nickel and copper. The typical value of strain that we measure with strain gauges is somewhere in this region. So let's say up to 0.5% of strain, maybe 1% strain. We simply want to avoid plastic deformation in the material, so we have a limited strain that's available. Here you can see the Constantan alloy, so it's has nice linearity here. It works quite well in this region. We can see another ferric alloy. It's not here in the table, but it has similar properties as this Constantan alloy. We can see also some other alloys like gold and palladium, but obviously this would be very expensive. So the same here, rhodium and platinum. So rare metals are not used for strain gauges for the reason of price and also the reaction on temperature eventually. So what is the basic resistance of the strain gauge? In most cases it is 120 ohms. So the resistance is specified for temperature 23 centigrade, and for this 23 centigrades without any applied strain we will have this 120 ohms. Also 350 ohms or 1000 ohms strain gauges are used, but there are less common than 120 ohms. So 120 ohms is the most common type, then 350 ohms, and then 1000 ohms. In all cases, we absolutely require temperature compensation, because if you do not compensate for temperature changes, then even if we use Constantan as the material, the influence of temperature will be very large, and we need to compensate for this temperature influence. And only when we compensate for this temperature influence we are able to measure actually the strain that we are looking for. To give you an example about this temperature compensation, let's take a look on this calculation. In this calculation I have used a steel bar. The steel bar has a cross section of 1 square centimeter. So this side here is 1 centimeter, and here we have 1 centimeter as well. And here I have installed 2 strain gauges. The first strain gauge, gauge 1, is made from Constantan. Constantan has this temperature coefficient of resistance, and the second strain gauge is made from copper. Here I have to stress out that this is a fictional strain gauge because copper is not used, and we will see soon what is the reason for that. Here you have the temperature coefficient of resistance, so you can see that compared to Constantan it's about 3 orders of magnitude larger. So if you have the same strain gauge made from Constantan and copper and the same temperature change, this copper will change significantly its electrical resistance. Now on this beam we have applied a force of 1000 Newton, so approximately 100 kilograms here, and we have a steel with this parameters. First let us calculate what is the strain and what is the change of electrical resistance. So this is a standard formula that allows to calculate tension stress. If we want to calculate strain, it's based on this formula, so it's the tension stress over this 200 gigapascal, that's a material constant, and we will get that the strain that we actually apply is 50 times 10 to the power of minus 6. So sometimes it's also called 50 micro strain. So it's not, this is a typical value that you can use for strain gauges. It's near the origin, so it's almost no deformation at all. And now if we apply this formula for the electric resistance, we will assume that the gauge factor here is 2. Then we'll find out that the relative change of electrical resistance is 0.1 times 10 to the minus 3. So it's a very small change of electrical resistance. Now this value of 2 is obviously not entirely correct, because this assumes a metallic strain gauge. but in my example I have used different materials. So this was Constantan, and this strain gauge was made from copper. But the actual values for the gauge factor for Constantan and copper are quite close. So for Constantan is 2 or 2.1 as we've seen in the table, and for copper it is 2.6. So this assumes that I have used only 2 here as the gauge factor. So it's not entirely correct, but we'll see later that this does not play a role at all, because the gauge factor of the copper will not be very important. What will be important will be the temperature coefficient of electrical resistance for the gauge factor. So if I calculate the resistance change in ohms, then here we have the gauge factor, we have the strain, and we have the initial resistance. I have chosen the 120 ohms strain gauge, and this will give us a value of about 12 milliohms. Again, this calculation is not entirely accurate, because for copper I would need to use 2.6, and here for Constantan 2.0 or 2.1. But anyway, we can see the range. Initially we had 120 ohms strain gauge, and this is a change that's about 12 milliohms. So now let's take a look at the output voltage. Now the strain gauges are typically connected in a bridge. We'll see that today as well. And one of the most simple connections is called a 1/4 bridge. And the output voltage is calculated by this formula. So this is the output voltage. Vs is the power supply voltage, K is the gauge factor, and this is the strain. I have chosen that my power supply voltage is 12 volts, that's the value here. This is the gauge factor, again I'm assuming Constantan, and this is my strain that we have calculated on the previous slide. So we can see that the bridge output voltage is about 300 microvolts. So it's a very small voltage, and we may have trouble in measuring this voltage directly. So this is a value to remember for the moment, so 300 microvolts. Let's take a look on the effect of temperature. Let's imagine that you have a beam, and this is your beam, and now the sun starts shining on the beam, or some other heat source will heat up the strain gauge. Now if you calculate the change of electrical resistance as per temperature change, you will use the temperature coefficient of resistance, alpha here, and for Constantan you will find out that it's about 10 milliohms. So it's approximately the same value as we have from the force. If we calculate the same for copper, we can see that here we have 4.7 ohms. And to remember that initially we had 12 milliohms from the force. So from the force our signal was 12 milliohms. We have changed the temperature just by 10 centigrades, and the signal from temperature is about the same size. And here for copper it's completely hiding this signal, so we are not able to use this copper strain gauge at all. So we can see that even if we use the Constantan for the strain gauge without temperature compensation, we will run into big trouble, because here this value only by 10 centigrades change is very significant, and it has almost the same size like the value created by force. And you can basically not distinguish if the force has changed or if the temperature has changed, unless you measure the temperature, for example, or unless you compensate for the temperature changes. So all the connections that I will show you today will include the temperature compensation, and without it, it is more or less like a thermometer, but it's not a force sensor. Let's now have a brief look on the semiconductor strain gauges. I recommend you to take a look on this website. They have very nice animations, not only for strain gauge sensors, but also other sensors as well. And you can see for yourself how the sensor works. Now here on this picture we see one of the possibilities how such a piezo-resistive semiconductor strain gauges can be created. So we can see that we may have it like a composite material where we have a polymer or thick film material, and here we have conductive particles, and when you press the material together, those particles are closer together and the resistance is decreased. In silicon there is another effect that takes in place, that's the piezo-resistive effect. In all cases, what happens is that the semiconductor strain gauges have some advantages and many disadvantages. One of the biggest advantages is that they have significantly higher sensitivity. So the gauge factor is significantly larger than for metallic strain gauges. It is approximately 25 times higher, so we have 25 times higher sensitivity. The gauge factor is typically larger than 100. So remember that here for the metallic strain gauges the K was about 2. For semiconductors it is larger than 100. However, semiconductor strain gauges have also many disadvantages, and one of them is that the function between resistance and strain is nonlinear. We'll see that on the next slide. So we don't have a nice linear response as we had in the metallic case. The second disadvantage is that we have a very significant dependence on temperature. So here this is the function resistance as a function of temperature. Not only it's non-linear, but also it is with a higher sensitivity than metallic strain gauges. So here we have about 75 times higher sensitivity on temperature. So if you remember those values here for constantan, then this value would be about 75 times larger. So then we may have again problems without temperature compensation, or if the temperature is changing in our application. But the advantage of the semiconductor strain gauge is also its size. The semiconductor strain gauge can be very small, so here this is just this bar of material. Here we can see the two terminals, and you can get the semiconductor strain gauges with or without the backing material. So it actually can be just this bar of the material where you can install it directly on your object. So the semiconductor strain gauge can be very small, and you can use it in slots, you can use it in holes, wherever you are limited in space to install the actual strain gauge. So a strain gauge with semiconductors is typically used in specialized applications where you are really limited by the space, or where you know that your temperature will not change, or where you need a very high sensitivity for the strain and you know that the temperature will not be changing. So here are a few examples. So this is a semiconductor strain gauge without the backing material. Here you have an approximate size, so there are many types that are available. So let's say the length is a few millimeters here. It could be something like between 2 and 20 millimeters approximately. And here you can see that the width of the bar is about 1 millimeter, but it can be as small as 0.1. So the semiconductor strain gauge really fits into very small space, and you can place it in limited space applications. It can be acquired also with the backing material. So this is the strain gauge itself, and then you glue the backing material on your object. when it's without the backing material, you glue the strain gauge directly to the object without the backing material. Again, special glues are used, and it's quite tricky to install those semiconductor strain gauges because it is quite fragile. It breaks very easily, and it's also very small to install. So typically the metallic strain gauges are preferred if we are not space limited. In those formulas, you can see the dependence on strain and temperature. So we can see that in both cases it is a nonlinear dependence. Here for the strain we don't have the single gauge factor anymore, which would be the C1 here, but we have a second constant, and here we have a second power of the strain. So this is a nonlinear dependence, and you can get the constants for the materials from the data sheets of the strain gauge or from the manufacturer. A very similar situation is then for temperature. Here this is temperature, and this is those are two coefficients A and B that correspond to the temperature coefficient of resistance, and we can again see that there is a significant dependence, a nonlinear dependence on temperature. So we will not use semiconductor strain gauges. If we will have the lab on this topic, we will just show you how they look like, but we will use metallic strain gauges. Okay, now let's take a look on electrical circuits that we can use for strain gauges. Remember that we are looking for a very small change of electrical resistance. So we will need a circuit that has an input as electrical resistance, and the output will be voltage. And this circuit needs to be very sensitive. This is such a circuit that you see on the screen. It is called a bridge circuit, and we will see few versions of this bridge circuit. Now the first one is called a 1/4 bridge. It's called a 1/4 bridge because out of those 4 resistors that you see on screen, only one is the actual strain gauge that measures the force. In my example, it is this one here on top left, and we can see that it has some initial resistance R0. This could be the 120 ohms, for example, and it is changing its resistance by some value of plus minus delta R. So this is 120 ohms, and this is a very small value that we are trying to measure. And this symbol here is telling us that this resistance is a function of strain. That's here the value. Now this bridge circuit is always composed of 4 resistors. In the 1/4 bridge, this is my strain gauge, and the other resistors here shown as R0 in this circuit are fixed resistors. So this is typically 120 ohms as well, 120 ohms as well, and the resistor shown here in red, the RC, will be the one used for temperature compensation. So all the circuits that I will show you will include the temperature compensation. Now the circuit needs to be powered somehow, so we need a DC voltage here, V, and if we will be calculating the properties of this bridge circuit, we should take into account also the internal resistance of this voltage source. So this could be an adapter, it could be a battery, for example, some kind of power supply that's supplying DC voltage, for example 5 volts or 12 volts, and this models the internal resistance. Now in the calculation we typically neglect this internal resistance Ri because it's significantly smaller than the values of R0. So R0 here is typically something like 120 ohms, Ri is something like 1 or smaller, so we can neglect that. Now the equation that you see on bottom is called equation of balance. and it is telling us when the bridge is balanced. Now the balanced bridge, it means that here the output voltage V0 or VO is 0. So here we measure the output voltage on those two terminals, and when the voltage is 0, then the bridge is balanced. And the bridge is balanced only if this condition is met. Now the orientation of the resistors is the following. Here this is R1, R2, R3 and R4. It's not shown here in the picture because we'll not need it right now, but just keep in mind that we can balance the bridge here to obtain 0 voltage. The way it's done is that typically those two resistors R0 and R0 here are not fixed resistors, but we can change the value, and then if we are looking to zero out this voltage, we are changing the value either of this or this, dependent on the configuration, until we have 0 output voltage. We will not do it, and we will use this in the unbalanced configuration, which means that R0 here is a fixed resistor. We do not change it, and we measure the voltage directly on the bridge output. But in this case, the dependence of voltage VO on change of delta R here will be nonlinear. So keep in mind that if you want a very accurate measurement, you should use a balanced bridge, where you are manually or automatically balancing the bridge and looking for 0, looking for a single value. And here you don't care about linearity because you're looking for 0. If you measure the voltage directly, then it's an unbalanced bridge, but VO, the output voltage, is nonlinear dependent on delta R, and it's significantly nonlinear. So even if you have some very small change of delta R, you will get a nonlinear response. Okay, so let's say that here we have some output voltage as a function of change of resistance. For the moment, it's not important what this voltage will be, but we can definitely look for the sensitivity of this bridge. In other words, if I apply some change of resistance, what will be the change of the output voltage? And let's say that the sensitivity of this 1/4 bridge will be 1. I will define it as 1 because I will compare all the other connections with the 1/4 bridge. Now let's go back to this resistor RC. In this case, it is a compensating resistor, and it's nothing else than a strain gauge. So in this connection, we actually have two strain gauges. One strain gauge here measures the strain, and this is a second strain gauge that is installed in our application. But the installation is done in such a way that it does not measure the strain, but it has the same temperature. And we will see the installation examples in a few minutes. So mechanically, this 1/4 bridge has two strain gauges, but one of them does not measure the strain, and the strain is measured by only one of the strain gauges. The second possibility is that we install two strain gauges. And the reason to do this is that we want to increase the sensitivity. We have seen in the calculation example that the output voltage of the 1/4 bridge is quite small, and we may have trouble in transmitting it for longer distances. It was a few millivolts, or in our calculation it was 300 microvolts. So if I want to increase the sensitivity, I have to increase the number of strain gauges. So we can use two strain gauges, so this will be called a 1/4 bridge, 1/2 bridge. and again it will be including temperature compensation. Now that we have two strain gauges that measure the strain, we actually have two possibilities, and one of them is that the strain gauges measure in the same direction. So for example, we install them in such a way that both of them measure tension or both of them measure compression. In this case, it's connected like this. So this is one strain gauge and this is a second strain gauge. Now if you remember the condition of balance, it was R1 times R3 equals R2 times R4. So if we install that on the same side of the condition of balance, which is here, then we increase the sensitivity because it will not cancel each other, but they will act together. So in the case of a 1/2 bridge with the same sign strain gauges, here is the position and here is the position. It would obviously work as well if we would install the strain gauge here, and those two resistors would be the compensating resistors. It's exactly the same. We are again looking for the output voltage, so this is the output voltage, and it will have some sensitivity when we are changing the resistance of the strain gauge. In this case, the sensitivity of the 1/2 bridge will be doubled compared to the 1/4 bridge. So by using two strain gauges instead of just one, we have doubled the sensitivity. So from measurement point of view, this is a 1/2 bridge because we use two strain gauges to measure what we want. But again, those two resistors RC are actually the other strain gauges that are used for temperature compensation. So in order to compensate the temperature, we already need to have 4 strain gauges. So this was the case when both strain gauges measured in the same direction. In some cases, you need a different configuration where the strain gauges do not measure in the same direction. That's, for example, when you have a beam and one strain gauge measures compression and one strain gauge measures tension. And in this case, you can still use the 1/2 bridge, but you need to connect them differently in the circuit. So this is such an example. Here we can see that one strain gauge is increasing its electrical resistance, that's here this plus minus, and the second strain gauge is decreasing its electrical resistance. So this would be a strain gauge under tension, this would be a strain gauge under compression. So for example, this would be the bottom side of the beam, this would be the top side of the beam. And again, we have two strain gauges here, RC and RC, but those additional strain gauges are only used for temperature compensation. So they have the same temperature, but they do not measure the strain. And we are looking for the output voltage. In this configuration, the sensitivity is also doubled compared to the 1/4 bridge. Now the last step is obvious. We already have 4 strain gauges, so why not to use them all to measure the strain? And this is the full bridge configuration. In the full bridge configuration, you use 4 strain gauges. 2 of them measure tension and 2 of them measure compression. So if you're not space limited and you can actually install them in this way, then this is the most sensitive connection, because compared to the 1/2 bridge, we again double the sensitivity. So compared to the 1/4 bridge, the sensitivity is 4 times larger. Now this obviously requires that 2 strain gauges measure in the same direction. So for example, those 2 would measure tension and those 2 would measure compression. Again, we're looking for the output voltage, and as I've already said, it has a 4 times larger sensitivity, so for compared to 1/4 bridge. The temperature compensation here is done automatically if all the strain gauges have the same temperature. So if all strain gauges have the same temperature and change the temperature in the same way, it will automatically compensate for the temperature. So for these reasons, the high sensitivity and automatic temperature compensation, the full bridge is the most common connection used for strain gauges. So in almost all applications you will find a full bridge connection. Here is an example with some values for the bridge. So in this calculation they have used a 350 ohms resistor. They have 350 ohms strain gauge. They have used the 10 volts power supply, and here if you launch the animation on the link you will see that those values are actually changing, and here we can see the output voltage. So the output voltage is still quite small, but it's 4 times larger than it would be from a 1/4 bridge. And here we can see also the values of the resistors. So here the change is a little bit larger, it's in units of ohms, but again compared to the initial value of 350 ohms it's still quite small. Here you can see the formula that is used to calculate the output voltage is nothing else than a voltage divider, and it's calculating the voltage on those two output terminals. So remember that full bridge is used almost exclusively because of the sensitivity and temperature compensation. On the other hand, you can the full bridge is more costly than the 1/4 bridge because you simply need more strain gauges, but the strain gauges are not very expensive. It's something like maybe €5 per piece, so it's not that expensive compared to platinum temperature sensors, for example, where we had a price of, let's say, €100 approximately. So how to install the strain gauge? Well, it depends on what do you want to measure, and based on this measurement you need to select the proper configuration. Now I will show you 3 examples. One will be for the axial force, one will be for bending force, and one will be for torque. In all those cases the connection will be a full bridge, and it will have therefore automatic temperature compensation. So this is how the full bridge will look like. So this is R1, R2, R3 and R4. It corresponds to the condition of balance, and here you can see the installation. Now this example is for the axial force when I want to compensate for bending force and torque. So I want to measure only FA, but I want to compensate for FB and eventually the torque here as well. So this is how it should be installed. So in this case R1 and R4, you can see if I apply force it will change the resistance of R1 and R4. So that's here in this part of this branch of the circuit, and this resistance will change, and R2 and R3 are installed in the perpendicular direction to FA, so they will not be affected by FA. So this connection will measure the axial force, but will not be sensitive for FB. Now when we assume that all those strain gauges have the same temperature, then it will automatically compensate for temperature changes as well. So this will give us very small sensitivity to temperature changes. For torque, it works in a similar fashion. If we try to apply torque to this beam like that, then R1 and R4 will not be sensitive to that because they are installed in the perpendicular direction. But it will be measured by R2 and R3, but one of them will see compression and one of them will see tension. So again, this will automatically compensate for the eventual torque that may happen in this application. Now here is a link for a video how to install the strain gauges. It has about 20 minutes, but if you are interested in the topic, then take a look on that. It's not as simple as just taking a strain gauge and gluing it on the surface. It requires surface preparation and so on. The second example that I will show you is how to measure the bending force. So here we want to measure FB, but we want to compensate for FA, and eventually, well, not eventually, but we want to compensate for temperature and eventually also for torque. So this is the configuration here. So all the strain gauges are now oriented in the axial direction. So if I apply FA, they will all stretch, but they will stretch equally, and then this bridge will stay in balance. And here, if we apply force FB, we will have R1 and R4 in tension, and R2 and R3 will be in compression. So this R1 and R4 will be in tension. That's one side of the equation of balance. So this resistance will increase, and R2 and R3 will decrease its resistance. So we will see an output voltage. For torque, again, it's not sensitive, because if we apply torque, then all the gauges are installed in the perpendicular direction, so they will not be sensitive for that. So if you are looking for bending force sensor, this is how it should be installed. Now the last example is how to measure torque, and we'll see this again in torque sensors at the end of today's lecture. Now this is a shaft, and here we are applying force, and we are trying to compensate the eventual axial force, the bending force, and temperature as well. Now from other subjects like elasticity of materials, you probably know that if you apply torque, then the direction of the main stress is under the angle of 45 degrees. So here we have an angle of 45 degrees, and this is a strain gauge rosette, and another strain gauge rosette is installed from the back side. So 45 degrees because of the main direct stress direction. Here you can see the 4 strain gauges. So again, if we apply torque, we will change the resistance of the strain gauge, and it will manifest itself as the change of voltage on the output. If we apply axial force, then we will stretch those strain gauges, but they will stretch in the same way on both sides. So again, it will cancel, and we will see no effect at all on the output voltage. The same applies for temperature and for the force FB. Okay, now let's take a look on how we can use the strain gauges in applications, and how it is installed on real devices. Now on real devices, you basically have 2 options. Either you use a load cell, which I will explain in a second what it is, or you install the strain gauge directly on your object. So if it's a beam, if it's a bridge, or if it's a piping system, whatever, then you can install it directly. If you want, for example, to weight something, then you need to use a load cell. So a load cell is the element where we measure the deformation, and we can use the load cell in a weight to weight goods, to weight cars, to weight trains, for example. So how is it working? Here you have a example of a so-called S-type load cell. Now here this has a letter S shape, so that's why it's called S-type load cell. And inside here we have a cavity with the 4 strain gauges. Again, full bridge is used, so it has the highest sensitivity and temperature compensation. And now if we apply force, then we will deform this load cell, this area here, and this will be measured by those 4 strain gauges. Now here you can see a real S-type load cell. So this is the S shape. Here under this cover there is the cavity with the 4 strain gauges, and they are connected in a full bridge connection. So here you can see the connection, and we can actually see that we don't use only 4 wires, but in this case a 5-wire connection is used. Well, 5 wires. We have 1 wire is a shield, or is the cable shield, and the 4 wires are connecting the bridge itself. In some cases, in specialized applications, it could be also a 5-wire or 6-wire connection. All this cavity here is hiding the strain gauges, and it's hermetically sealed. So there is no access of water vapor or some other gases that would damage the load cell and the strain gauges. So this is typically welded during production, and then this is for example, a stainless steel cover. Here is another type of load cell that is quite common. You can find that in weight applications. It's called a beam load cell. Again, here we have a cavity with the strain gauges. Again, it's a full bridge connection. Well, in this case, the strain gauges are mounted from the inside of the cavity here. There are, let's say, less expensive applications for normal environments where the strain gauges are installed also from the outside of this hole, and then they are covered with a special covering material. So it is again a full bridge connection. The way this beam load cell works is that one side is attached to a fixed frame. It is this part, so this is attached to a platform, and here this is attached to another platform, but this platform can move up and down, and you can actually place some objects on this platform. This beam will bend, and this bending is measured with the strain gauges. So you can find this in kitchen weights, you can find this also in larger weights, so it's typically for weight applications. And last example is the so-called compression load cell. Now here we're not bending anything, but we are compressing the material. The compression load cell is typically used for very large forces. So if you want to weight a truck, or if you want to weight a train with a very large force, then the compression load cell can be used. The way it works is that here you have a cylinder that on one end, and this end, is attached to your object, and here on the other end here is attached to the frame, so to this platform which is mounted somewhere in the machine. And in this case the strain gauges are mounted in the vertical direction, so like this, and we are only compressing them. So in compression the materials can work with very high forces before they will break. So we are just compressing the load cell, and this allows us to measure the large forces. For example, this here you can see 10,000 kilograms is the range. Here you can see another units, but it's in principle it's the same type of load cell. Let's take a look on some applications where you can use strain gauges. So obviously for strain analysis You can measure strain or on a railroad track, so if you want to measure the deformation, if you want to count cars, if you want to measure the weight of the train, then this is how it can look like. So you can see here the strain gauges, and here as well. In all those applications, the strain gauge needs to be well protected against environmental effects, so against moisture, against rain, against changes of temperature and so on. So when you install the strain gauge, you need to cover it quite well with some covering materials that are used for this application. Here you can see some pins, and again strain gauges mounted on different positions. Again here some shaft that has mounted strain gauges. It could be, for example, to verify the finite element model that you have made for this object. Few more examples. This is bike with special frame where they used strain gauges to verify the calculations. So we can see here strain gauges mounted in different positions whenever they needed to verify the strain on the construction. It's possible to measure other objects as well. So here we can see a case of some machine with many strain gauges. Here again some shaft. Here you can see some bearings. So the examples are very various, and it depends on whatever you can measure. But by the way, on all those examples, only foil strain gauges are used because those are really the most common ones. A few more examples. It is possible to measure on rotating objects. So here this is an example of looks like a torque sensor or force sensor somewhere. So this is the strain gauge here on one side, another strain gauge would be on another side, and this is the bridge plus the wireless transmitter and battery. So you can install that also on rotating parts. Another example here is some looks like compressor blades, strain gauges installed at the positions, and here it goes to a wireless transmitter and that transmits the data. It's also possible to measure on non-metallic materials. That's shown here in this example. So this is a composite material, looks like carbon fiber, and here you have the strain gauges that measure the strain, and those two strain gauges, you can see they are separated from the base material. So those strain gauges are used for temperature compensation. So they have the same temperature, but they are not affected by the strain. So here those four strain gauges are the compensating ones. So it looks like that this is a half bridge connection, where here we have the two strain gauges that measure the strain, and this is the compensation, and again here another half bridge, again compensation and measurements. You can find strain gauges in weight applications. So if you take normal kitchen weight, for example, then in most cases you will find something like this. This is the beam load cell. Here it is attached to the frame, and here it is attached to the platform where then you put your ingredients and you weigh what is their weight. It is a full bridge connection, and here this is the cavity that actually allows the beam to be deformed. And strain gauges are in some cases placed from the inside of the cavity and then welded shut, or in some cases it's installed on top and on bottom of above and below this cavity. Here you can see a few more examples. Again, it's a weight. So here you can see the object that actually gets deformed, and here is a detail with the strain gauges. So actually this part and this part gets deformed when you apply some weight, and it's measured. So it's quite simply used. Those beam load cells are not that expensive. I think you can buy a load cell like this for a few kilograms already with the 4 strain gauges in a full bridge connection for something like maybe $5-10. So it's not very expensive at all. So here are a few examples of installation of strain gauges. Here is a link where you can find more info. So here they have installed the strain gauges on a piping system from a hydropower plant from France. Here you can see the installation. So this is the basic material, the metal where the strain gauge is glued, and then for protection from environmental effects, it is covered with many layers of protecting materials, and then at the end it looks like this. This is the cable that goes to a transmitter, or it could be a data logger, for example. Here is another interesting application. Strain gauges can be used to measure residual stress after heat treatment. The way it works is that you install a strain gauge rosette like this on the object, and then you start drilling or milling the hole in the object itself. We'll see that in this animation. And when you drill the hole in small increments with a specified speed, then the stress will be released at the location, and it will be measured by the strain gauges itself. Obviously this is a destructive test, so it will destroy your object. You will have a small hole in there, and it's a one-time measurement only, so you cannot repeat this measurement at the same position. You need to install another strain gauge rosette and drill another hole at a different position. Last example, again, weight application typically. Here there is an interesting note about that. They are saying that after, say, refurbishing of an airplane, you need to center the center of gravity again of the plane, and here you can see such examples of a weight that the plane rolls on the weight, and you can measure the weight distribution under the different wheels and change the center of gravity like this. There is a very interesting video. I will again not launch it, but you can take a look on it. How truck scales are made. It is showing how the strain gauge is produced, and then how it is installed in a truck weight and how this works. So it's a quite interesting video, and I recommend you to take a look on that video. At the end, let me tell you something about how to select and how to install the strain gauge in your application. So first of all, we can base our selection on geometry. If the direction of the main stress is known, then we can use a single axial strain gauge. If we want to measure just in a single axis, so then we use a strain gauge that looks like this. If we want to measure in both directions, but we already know what is the direction of main stress, we can use a 90 degrees rosette. So it looks like this, 90 degrees strain gauges, 2 of them. If we do not know what is the direction of the main stress, then we can again use a rosette, but in this case 120 degrees, and it's possible to calculate or prove mathematically that if you measure the stresses in 3 directions like this, you may actually calculate the direction of the main stress. So then you can go back to this step and measure again if you need it, just with this two strain gauge rosette. So that's one possibility how it can be selected. Another possibility is that we may base our selection on some limitations that we have in the application, and typically it's dimensions. So if we are limited by dimensions, then there's no escape from that. We simply have to fit our strain gauge where we need it. So this is an example. Here you can see a shaft with a slot, and we want to measure the strain in the slot when we apply some force. So we are limited by the length and width and height of this slot. So this is where the semiconductor strain gauge may come in handy, because it may fit in this limited space. If we are not limited by dimensions, then we may be limited by the homogeneity of the material. It simply means that the material can be a composite material, for example, and that here those particles may affect the measurements. So in this case, we need to select a quite longer strain gauge with a longer grid, because we want to calculate a kind of average over this whole length. So it's not correct to select a short grid like this, because you may place it over the inhomogeneities that you have in the material. So it is recommended that this length is larger than 5 times the size of the inhomogeneity that you have in your material. Well, if you have a homogeneous material, then you are basically limited by the length of the strain field, so it means where you actually want to measure the strain. So based on those criteria, you can select many types of strain gauges, a strain gauge rosette, as we have seen in the many examples. Now at the very end, let me show you a little bit about torque sensors. Now it's very simple, because torque sensors will use strain gauge rosette. A strain gauge rosette will look like this, again 45 degrees because of the direction of the main stress. And this is an example where we have a shaft and we want to use this as a torque sensor. So this object is rotating. Now this is a full bridge. Here you can see how it is connected. And we basically need a power supply, so we can have here kind of transformer that through the air gap provides us power supply, or it could be battery powered as well. And this is a converter that actually produces DC voltage for the bridge, because the DC bridge needs a DC power supply. And then we need to get out the voltage here somehow. So either you can have a DC to AC converter, which converts this, for example, to variable frequency, and then it's transferred through capacitive or inductive coupling from the rotating shaft. Or this could be all this, it could be a transmitter, wireless transmitter with an antenna, and again it measures the voltage and transmits us some number. Here are a few examples how those torque sensors look like. They are quite expensive. You can see the prices on screen. There is a big difference between the fixed and rotary torque sensors. The rotary sensors are approximately 10 times more expensive. And if it's just a fixed sensor here, you just attach this with the armature somewhere, and here on this part you have the strain gauges, so it's less expensive. This is an example of a rotating sensor. The shaft is attached to the motor and to the couplings and to the load. And here this is the assembly, where on the rotor you have the strain gauges. So on the rotor you have this part of strain gauges, power supply, and some transmission of the data outside. And then this is picked up in the stator that provides power and gets the data. And then you have some output signal. It might be a digital bus, or it might go to some meter that looks like this and shows you what is the actual torque. Again, there is a quite nice video here about those torque sensors. Last slide. Here you see a few examples of applications. So torque sensors are typically used to measure torque between the electric motor and a load. So you see such an assembly here. This is an induction motor, this is the load, and here this is the torque sensor, so we can measure the torque. Here you can see a very large torque sensor for 1.5 mega Newton meters. Again, there is a link for that application, or I believe they're saying it's used to measure torque in ship applications. And again, I recommend you to see this video about how the torque sensors are actually used.